Hi again, guys. So now that you have a little bit of background in stats and why it's important and how to interpret p-values, I want to walk you through a little tutorial that will help get you up and running for the data that you'll be working with. So if you navigate to the content section of D2L and you go to this week's lab, statistical analysis, and Darwin's finches, should have already done the pre-lab stuff. The data I'm going to show you comes in this Excel spreadsheet, frogs, example data with t-test steps. Your assignment then will be to work with this finch data set. So there's a PDF document that will walk you through what's going on and then the data set for the finch data. But for now we're going to look at this frog data, so you can download that and work along with me. I encourage you to do that, so watch what I'm doing and then do it yourself on your machine, so kind of going back and forth between the spreadsheet and this video. So I have the data set open here. Once you pop it open, this is what it should look like. So in our scenario, we know that an ecologist has been studying a couple of frog populations that live in two different microclimates. So one population lives in a wooded area, that's this data set here. A second population of frogs lives in a river bank area. We know their diet is a little bit different because there's different insect species in the two areas. And we have data for the weight of frogs in these populations. And each population has 20 frogs that we are dealing with. And we've recorded the weight of those frogs. And that's the data here. So we are to run a t-test to determine if the average weights of two frogs are statistically different. And we're to include a few other pieces of information here. So first, be sure to define your null hypothesis. So think about what this is, and then you can type your null hypothesis here. So again, remember your null hypothesis means what? That there's no difference between the two frog populations. So null meaning that there's no difference between frog populations. We could get a little bit more specific, and it would be good to get a little bit more specific and say that there's no difference in the weights between these two frog populations. So first we're asked to calculate the mean of each data set, or the average of each data set. So you should remember how to do this from last week's Excel tutorial. So remember the average function. And we're wanting the average for population 1, so we can simply highlight all of that data, click enter, and that should have filled in our information here. We could do the same thing for population 2. Otherwise, we can do a little shortcut and just drag over. We see a new number popping in here, but if we take a look at what's going on, you can see that Excel has just kind of copied that information here, but moved it over, shifted it over. So we're now dealing with the information for column B. You see we have all the data we wanted selected. Pretty easy. Cool. So now we want to know the variance, or the spread of each population. So Excel has formulas for variance. Remember we discussed this in the last video. So we can either use just plain old equals VAR, or use alternatively VAR.S, so that's the variance of our sample population. We get 10.7. Do the same thing here, spread that over. Looking at this data, we see that there's a little bit more variance in population 1 than population 2. Next, we're asked to calculate the standard deviation. So, formula for this, it's equals ST DEV. So we have a few options for standard deviation. Again, either just use the regular STDEV or STDEV.S for our sample population. Again, using the same chunk data. Oops. Looks like I didn't quite get everything that I needed. Try this again. Oh. Let's just undo things. Control Z is a great way to undo things if you need to. Alright, so now we'll try. And now we have our data set here. We can copy that over. So the standard deviation for both of our populations. So now we're asked to calculate the standard error. So standard error is fairly similar to standard deviation, or it's related to standard deviation, and you can see that in the formula. So standard deviation is simply, or standard error rather, is simply the standard deviation divided by the square root of the number of individuals in our sample. So in order to calculate that, we can just put in our equal sign, and we know we want to divide the standard deviation, so we've calculated that here, by the square root, SQRT is our function for square root, of the number of individuals in our population that we're dealing with. So we said that we had 20 frogs in each of our populations, so square root of 20. Close out with another parentheses, and we should get a value of 0.7318. We can carry that over to our second population. We should have the same thing there, that 20 individuals has carried over as well. Next, we're prompted to calculate a confidence interval, or a 95% confidence interval. And I'll talk about what this is in a second, but first we'll calculate that. And we simply see that the confidence interval is 2 times our standard error. So we can just do equals 2 times, 2 times the value we got for our standard error. Oops. So 2 times what's in cell D7, carry that over as well. So 2 times, in this case, what's in cell E7 for our standard error. And those should be our values for the 95% confidence interval. So just to back up and talk a little bit more about standard error and these 95% confidence intervals. So keep in mind that when we are sampling individuals in our population. So in this case, we've sampled 20 frogs randomly from our population. We're just taking a random sample of all the frogs there. If we had sampled another group of frogs, we would have probably gotten some different frogs. So there's probably more than 20 frogs in our population. So we'd have gotten a different 20 frogs if we, just by random chance, we ended up getting the frogs that we did. So it's not really possible to know with a high level of accuracy that the mean that we calculated for our sample is the exact same as the mean of our entire population. We're estimating the mean of our population here. So the standard error of the mean shows how close our sample mean is to the population mean. So if we took a lot of random samples, our standard error of the mean, which we calculated here, should approximate the actual sample mean. So then with the 95% confidence interval, that confidence interval shows the range of values, or helps us to estimate the range of values where the true mean should lie. So what we're saying here, so if we use this for an example, our sample mean of 22.07, the true population mean should be within plus or minus 22.07 plus or minus 1.27. So it should be plus or minus, or 22 plus or minus 1.27 grams. So narrow there. This one, likewise, we're 95% confident that the true mean weight for our frogs is 25.15 plus or minus 1.46 grams. So the true mean should be within, what would that be, about 23.5 grams and 27.5 grams approximately. So now we're ready to conduct our t-tests, and think for a second whether we would use a paired or unpaired t-test. If you said unpaired, you're correct because we're dealing with frogs in two entirely different populations. So we'll use unpaired. This will show how to do that. Just for purposes of this class, always use t-tests with equal variance. I'm not going to go into details there. And now we want to conduct our t-test. So Excel has a formula for t-tests as well. And t.test is our formula, and we want to run a t-test on comparing population 1, our array 1. I'm going to pop open this formula bar here. So array 1 is our first population. And we're comparing that array to array 2. Oops. Let's start over here. T-test. And we're going to take all the data in array 1. And then we're going to compare that to array 2. We want a two-tailed test. That means we're interested in any sort of difference. So for this class, we'll usually use a two-tailed t-test. And we said we are dealing with, so for the type, this is the kind of t-test. If we had a paired test, we would put 1 in this blank. We don't have a paired. We said it was unpaired. So, and we said equal variance. So we want a two-sample equal variance test. So we type 2 there. And now we get our p-value. We see we have a very low p-value, 0.0029. So that's below that 0.05 threshold. So we would say that that low p-value leads us to reject the null hypothesis in favor of the alternative hypothesis. So there is a significant difference between these two populations. And our steps to the run a t-test are here as well for you to review. Next, we want to create a graph of the means of the two data. So we're not going to graph the entire data set here. We're just going to graph the means of our two populations. So we can insert a graph, just use a simple bar graph. We get something like that. Population 1 and population 2 here. We want to make our graph a little bit more easy to read. So we can put in some axis titles, maybe a horizontal axis title, vertical axis title, and a chart title. So something informative. So now we have some catchy axis titles. We can also alter these 1 and 2 to make them more informative. If we go to right-click, and go to Select Data, and Edit, we want to capture these names, Population 1 Wooded, Population 2 Riverbank. There we go. So now we have a very informative graph that anyone can interpret. So now your task is to do some very similar things with this Finch's data set. So this is what that data set looks like. If you scroll to the bottom, you can see I asked you to do some very similar things. Calculate these parameters, run t-tests for each pair of data, and then analyze your results.